Sam, are you ready?
I'm ready. Great. Well, thank you very much, Laurent, for the kind introduction, and Juniper and Antoine, the rest of the organizers, for all of your hard work pulling this off. I realize that I think all of us wish we were together in person for a whole variety of reasons, not the least of which is that usually this happens before the semester starts. And so like we're relaxed and we're feeling good and not stressed about all of the meetings that we had to cancel to make this happen. But I do think that even though we have spent a lot of time on Zoom over the past year and will into the months going forward, that it's important that we continue to do these kinds of things so that we can keep building our societies and relationships and collaborations and supporting all of us as we, move forward with our careers in terms of building the relationships that matter and learning and starting new projects. So I really appreciate all of you being here and taking the time this morning. So let me share my screen. And all right, so everyone can see my screen and the slides are advancing.
Yeah.
Great. Okay. So yeah, just very, very briefly, the only additional thing I'll add by way of introduction is that Laurent mentioned that I used to work on fish, and I actually started as a greenhouse biologist in undergrad, working on plant quantitative genetics in the field, in the lab, in the greenhouse. And I started my PhD thinking that I wanted to be an empirical and field population geneticist. And that's what I did for the first half of my PhD. And, effectively retooled as a computational and applied math interested researcher starting in the second half of my PhD, and continue to learn and benefit immensely from my collaborators like Laurent and Antoine and Jean-Gab and others who are on the call that have so much more background in that area and those areas than I do. And so one of the things that I would encourage all of you to continue to remember is that it's really never too late to make drastic evolution in the kinds of projects that you're working on and the kinds of skills that you have, but that attending workshops like this, it's important in terms of what you learn, but I think it's more important in terms of the networks that you build so that you have those collaborators that can help you either learn new skills as you realize that there are things that you want to understand better, or who can just be on the papers and, do it for you, with you as your collaborators. So I think that that's kind of an important message. Okay, so the talk, I have too many slides because I kept realizing that as one of the first speakers, there's a lot of material that many of you probably haven't been familiarized with yet. And so I'm going to go really fast through some of the introductory pieces. And that's not because I think all of you will know it or expect that you will. It's that I want to kind of give you an overview of some of the terms that you may hear so that you at least have the questions in your head for what you want to learn more about or ask and answer. So
are slides supposed to be advancing right now?
No.
Okay, good.
So the thesis of the talk is that COVID-19 became a pandemic because the world doesn't understand complex systems and networks. And by the world, I also include all of us on this call, many of whom have contributed intellectually to improving our understanding of COVID-19 as it pertains to its pandemic potential and epidemiology, because it turns out that it really challenges so much of our modeling and our understanding of the world and human systems and human social and technical systems, even for those of us that have spent large parts of our career trying to challenge and relax those assumptions. And so what do I mean by that? Well, what I mean at a very high level, and we'll drill in as we go through the slides, COVID-19 is a complex system in that we have features of its evolution, features of our human social networks, features of our behavioral response, of our societies, for example, as it pertains to inequality and racism, xenophobia. All of these interact to result in this emergent property, namely a pandemic. And they interact in such a way that we have a whole list of countries from Vietnam, Thailand, China, Taiwan, Senegal, Nigeria, Australia, New Zealand that basically have not experienced a pandemic. And other countries like the United States, UK, Italy, that have been completely devastated by COVID-19. And that in particular, COVID-19 seems to be a pathogen that feels the effects of all of these different components very, very acutely, and that feels the effects of different scales from the macro level, thinking at the country, as you drill all the way down to the local level, you continue to have these effects persisting as you zoom in and zoom out, which is not necessarily the case, or at least is not obviously the case with many of the other pathogens like Ebola and influenza, for example, that we've responded to and tried to understand in the past. So this slide I borrowed, sorry?
I think we're still on the title slide.
Okay, so they're not advancing. Okay. Let's see. Oh, I understand that. How about now?
Yes.
Okay. All right. So, I copied this slide from Brennan Klein, who recently finished his PhD at the Network Science Institute at Northeastern, and has been a regular feature of the Complex Networks Winter Workshop. So being a little bit more specific about complex systems and networks as it pertains to infectious diseases, the transmission of infectious diseases we should think of as something that's heterogeneous. Oftentimes, few people infect many, many people. It's especially the case for COVID. They're highly dependent or can be on spatial structure, the underlying population, how people are distributed in space and time. They're unequal in terms of who they impact, effects of racism, income, inequality, age, etc. Will alter the course of the epidemic in terms of who it's infecting and how severely. And that as a result, we should best understand, or can best understand, this is a network phenomena where we have many interacting components, both from a social network perspective, but also from a behavioral perspective, a population perspective, that interact to result in these emergent properties that we care so much about, or that we feel so acutely, in particular, the pandemic that we're dealing with now. And most of what we're building off of from COVID-19 comes back to the SARS outbreak in 2003. And it turns out that a lot of the lessons that we learned or failed to learn from SARS, we're still dealing with both scientifically and as a society today. So here's an example of an individual receiving a temperature screen for SARS. One of the things that's true about SARS is that individuals are not, or thought not to be, infectious until they have symptoms. It's the same with Ebola. That is not the case for COVID. That's not the case for influenza. And it turns out there are features of the biology of pathogens that matter immensely in terms of our ability to control them. And so one of the things that's critical, and one of the reasons why we have to conceptualize this as a complex system or complex network, is that there are aspects of the biology of the pathogen that we cannot disentangle from the emergent properties in terms of its pandemic potential or its epidemic. However, this quote to me kind of encapsulates so much about what the majority of individuals engaged in epidemiology are still struggling to understand, which is that at the height of the pandemic, one Canadian infectious disease expert who had come down with SARS herself predicted that the virus would spread around the globe. And I'm quoting now, "If we don't have a vaccine, yes, we are all going to get it," she told Canadian television. Her opinion was shared by many that spring. And this opinion comes from the expected number of secondary infections for SARS. So very early on, individuals studying the epidemiology of this disease noted that the average number of secondary infections, the average number of infections resulting from a single infectious individual, was high enough that it should be able to cause a pandemic. And it, of course, didn't. And the fact that it didn't highlights the key features of the sociobiology of pathogens, in particular pathogens like SARS, namely that you have to account for many of the salient features of the way in which the pathogen is moving through the population if you want to translate aspects of its biology and our sociology into aspects of the risk of emergent properties like it causing a pandemic. So it turns out that this individual was wrong, not because of necessarily our interventions, although they were successful, not necessarily because of the fact that we were able to use temperature screens, but because SARS was so heavily reliant on large super spreading events for sustained transmission that the probability that it would cause a large epidemic was very brittle. It was highly dependent on lots of these rare events being strung together in very unlikely ways. And so the way we could conceptualize this is that the average number of secondary infections was being driven by these huge super spreading events. So this is an example of a cluster of 205 cases in Singapore, where you essentially had 5 individuals that actually did all of the transmitting that resulted in these 205 cases. And so the average across all these 205 individuals may be close to 1 or 2 or 3, but it's as a consequence of 5 or so individuals that resulted in a huge number of secondary infections. And for me, one of the most influential papers on my career, and I think in network science, was a paper by Lorne Myers et al. Called Network Theory in SARS, Predicting Outbreak Diversity, where Professor Myers, who was at Santa Fe at the time, showed that if you took the early case data, largely coming from crowded apartment buildings, areas where there were faulty ventilation systems leading to super spreading events, if you took the early case data and conceptualized it as a network model, where you actually account for the heterogeneity in social contacts, you account for the heterogeneity in secondary infections, you end up with a much more realistic expectation of the risk, namely that it's much more likely that a disease like SARS is going to die out on its own, and that you end up with much more appropriate measures for control, contact tracing, case investigation, the importance of testing, tracing, isolation, and quarantine, and reverse contact tracing, case investigation. And so this is what builds for a lot of our interest in epidemiology as it applies to networks. It's this intersection of both understanding more about the biology, physics, sociology of these pathogens, but also leveraging what we learn about them to improve public health decision-making, to improve our response. So by conceptualizing the spread of SARS as a network, we both improve our understanding of SARS, we improve our understanding of the way infectious diseases operate from a physics perspective, but it also motivates realistic and applicable public health interventions that can and are actually implemented and used to control pathogens like SARS and like COVID. So many of the strategies that we saw deployed effectively in places like Japan, so reverse contact tracing and cluster busting, are motivated from network science and from lessons learned in SARS about the importance of super spreading for diseases and how you actually have to modify your public health behavior if you're going to control them. However, it's unfortunately not so simple. And so what do I mean by that? Well, here's a picture of an individual with 1918 influenza. Here's a picture of individuals responding to the Ebola outbreak that Laurent mentioned in West Africa, 2014-15. It turns out, and I haven't really defined this yet, I'm going to in the coming slides, that the average number of secondary infections for both of these two diseases is approximately 2. Now, for those of you that understand this, of course, I'm sweeping a lot under the rug here that of saying something that's approximately the same for a nonlinear system is approximately inaccurate, but they have about the same, up to sampling error, average number of secondary infections. But flu in 1918 infected about 500 million people, and Ebola, while devastating to West Africa and to our global economies, infected a fraction of that. And this is not because of interventions. This is because of differences in the biology of these two pathogens and how they interact with our social networks, namely that Ebola is much more reliant on super spreading than influenza. And so this difference between Ebola and flu has motivated quite a bit of historical work, both in mathematical epidemiology and in network science, which I'm going to walk you through very briefly. But quickly, by way of introduction, we'll get some basic terms here. So one of the standard ways that individuals try to simplify the complexity associated with infectious disease modeling is to bucket individuals into categories or compartments, which is why it's referred to as compartmental modeling, if you've heard that term. And so we could think of the population as everybody who's susceptible, meaning they are not yet infected, but can be, as susceptible. And we can model the rate at which individuals become infectious, meaning that they are exposed and then they are infected and then they can infect. We can model that, at least initially, as what's referred to as a mass action process, where the rate at which individuals bump into each other, we think of this as happening randomly, the way we might model an ideal gas, the molecules bumping around into each other in a room. And so at some rate, individuals bump into each other with some probability they infect each other. We collapse both of those into a term beta. And then the movement of individuals, the progression of this system is governed by this parameter beta, the proportion of individuals that are susceptible and the proportion that are infectious. And then if we're interested in a process where individuals recover or die, we could think of this as a socially independent process, namely it occurs at some rate gamma that's independent of social contact. And then so at some rate gamma, individuals move from the infectious class into the recovered class. Now, one of the reasons that this is useful is that it provides both a visual way of representing the complexity, which helps our brains, and kind of a playbook for how you translate those into ordinary differential equations or computer simulations so that we can study the process mathematically or computationally. And so in the case of COVID or Ebola, we might add an exposed class. There's a period of time in which individuals are infected but not yet infectious and able to transmit. For diseases like pertussis, where we think that transmission may be very important from infants, but you have protective antibodies from the mother, we may have a period of time where an individual is born and has passive immunity, and then that immunity wanes and they become susceptible and they become exposed and they become infectious. And we can take all of these and write down a system of equations that describes mathematically what we're showing pictorially here is how individuals progress, or what is the rate of change of individuals in these different compartments as this system evolves in time. And of course, and you've probably seen this, that we can then layer on sort of like arbitrarily complex properties into these models. So we could have different kinds of infectious individual, we could have different kinds of recovered, we could have many different vaccines. And so while this may very quickly seem like we're heading towards agent-based simulations, I think one of the reasons that this is still beneficial is that this allows us to go through kind of a structured reasoning process where we either enumerate or draw on a piece of paper or whiteboard or on our computer the features that we think are important. And then we can use these as a way to generate hypotheses, to study the dynamics, to study the behavior of these mathematical systems, and maybe learn more about which of these components are more or less essential. So this average number of secondary infections, you could kind of think about it as the expected number of secondary cases in the beginning of an outbreak. The actual definition is probably a little bit more like the expected number of secondary infections if a single infected individual is dropped into an infinitely large population of susceptible individuals. That's the R naught. Any other number that you hear is going to be the RT, which is the kind of time evolving average, or the R effective, which would be a snapshot of the R at a particular time after the system has started evolving. And so for this very simple model where people bump into each other like ideal gases, the average number of secondary infections is going to be the rate in over the rate out, which reduces to beta times S divided by gamma. And so one of the reasons that we kind of like the R naught is it provides a way for us to compare these different models to each other. And so I have, these massively complex models, and Jean-Gab and I cannot agree on which one of these are more important, but we can kind of reduce them all down to a single number, which is we can enumerate the rate at which individuals come into the infectious class. It may require a lot of equations, a lot of arrows, and the rate at which they flow out. And then we can do some division and a little bit of algebra and come up with an equation that would maybe compare my R naught to Jean-Gab's R naught, and we see which of the different parameters are contributing in which ways, and it allows us to start to have a conversation about how these different features are contributing to the change in epidemic risk. And so why am I calling it the change in epidemic risk? Well, in a deterministic model, in an infinitely large population, if the R naught is greater than 1, that means individuals are leaving more than replacement number of infectious individuals. So I'm at least replacing myself and then a little bit more anytime it's greater than 1. And so we would expect that a large fraction of the population would become infected, and we refer to that as an epidemic. And so for a network model, we might say that would be the emergent of a giant component, meaning an infinitely large connected component if we're thinking about this as a percolation process. So it also provides a rough guide for thinking about what is the risk of an epidemic in the population. And then you might imagine that it also provides some mechanisms by which we could think about interventions, right? So if we can increase the recovery rate, we can decrease the susceptible individuals, we can decrease the rate at which individuals come into contact with infectious individuals. All of these things, we can decrease the per contact probability of transmission. All of these things will lower the average number of secondary infections and can contribute to the control of the disease. So this is going back to my initial statement, which is one of the things we're trying to do is both learn more about the biology, the physics, the sociology of these systems, understand something about what is often quite interesting, beautiful and fun math and computer science or computational algorithms, but then motivate public health decision making and demonstrate the utility of this complex systems or complex network style of thinking. So just an example of some R-naughts. Diseases like measles, whooping cough, chickenpox, polio, and smallpox have R-naughts that are completely through the roof. A single infected individual may be infecting on average 5, 10, 15, 20 other people. As I mentioned, for flu and Ebola, the R-naught is somewhere around 1 to 2 or 3, and it's in the same range for COVID. But as I mentioned, there's a problem. And this problem cuts to the heart of the issue with many of the things that probably some of you are already thinking, which is populations are not infinitely large, and that sometimes matters a lot. Sometimes it doesn't, but sometimes it does. In this case, it does. The world is probably not deterministic, or at least we are not able to figure it out sufficiently well that we can make it be deterministic. We almost certainly do not bump into each other at random, although sometimes we do, as we've seen with COVID and other diseases. And so as we think about all of the ways in which we might imagine the assumptions not being realistic, we wonder, is that contributing to the difference between Ebola and flu, and how? And so how do the intrinsic properties of the pathogen, the behavior, sociobiology of the host, how do they interact to break these simple equations that I walked you through and assumptions that I walked you through in the beginning, and necessitate the use of more complex approaches, more complex models when we are thinking about these different pathogens. And so briefly, then maybe we start by just conceptualizing transmission as something that happens on a network. So instead of saying people are going to bump into each other at random, we'll just put edges between nodes and we'll have a social network and we'll model the process of disease transmission on this social network. So now we think about a node as an individual, an edge in this case is a contact that is going to allow for transmission. And that's actually a really important feature that I won't say again, but is something that actually would be very interesting to work on as a potential project idea, is that we go out and measure social networks. And it's not the case that all or even most of those edges are going to be relevant for the transmission of many pathogens. And it's also not the case that all edges are even approximately equal in terms of the probability that a pathogen would transmit along those edges. And so it actually turns out to be really important how we conceptualize which edges in a network are going to matter and how in infectious disease processes, or honestly in contagion, in any kind of contagion process over a network structure. But here, edges mean that contagion can propagate. Nodes are individuals. I've colored individuals in blue that can become infected and are susceptible. Individuals are in red if they're infectious, and they're in this kind of tan color if they're recovered. And kind of the simplest approximation then for the average is that we're going to have this decomposition of this term beta. So beta before we could think about as having a multiplication of some mixing rate rho and some per contact probability of transmission t. And now we're going to have this same per contact probability of transmission t, but instead of this mass action mixing rate rho, we're going to use a little bit of network here, which we're going to have the mean degree k and the mean squared degree. And we can use those to take a very simple approximation of the average number of secondary infections. Again, this is assuming an infinitely large network and all the other things. We haven't gotten to relaxing those yet. But one of the nice things about the R0, and trust me, I'm going to come after R0 here in a second in a heavy way. But one of the nice things right now is that I can still compare my model to Laurent's model even if Laurent is using a network model and I'm using a non-network model, because there's a way in which we can translate both of those models into this same quantity. And I can see, okay, well, how is Laurent's assumptions about the network structure? How do those relate to his R naught? What's he assuming about the degree distribution, the clustering and other things? And how does that relate? So just as an example, kind of this is the difference between these two very simple models. So formalizing a bit more of this complexity, that's one of the things that we immediately then have to deal with as soon as we get into the network model. So you could imagine one way that I could write down a system of equations for a network is I could have a separate line for every different degree in my network. So I could have the evolution of susceptible individuals with degree 1, the evolution of susceptible degree with 2, 3, 4, 5, all the way up to degree K, which will be my largest degree in the network. And I would do the same for infectious and the same for recovered. And then I would have the pairwise evolution of the individuals that are susceptible with a degree 1 connected to infectious with degree 2, and all possible combinations all the way up to the entire system size. And so you might imagine very, very quickly, I'm just going to run an agent-based simulation of this. And so quite a bit of the formal work that's done in network science around infectious diseases is trying to understand how we can take creative and justifiable approaches to simplify the system. And there's a very nice review by Miller and Kiss in 2014 that I would point you to that at the time walks through the most common ways in which individuals will simplify the system. And so I'm showing an example here of the pairwise approximation where you say, okay, let's just pay attention to the time evolution of the individual degrees, so susceptible of degree K, infectious of degree K, recovered of degree K, and the pairs, susceptibles of 2 different degrees, susceptible, infectious, 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 and we're going to ignore the triplets and the quadruplets and all the way up to the n-tuplets combinations, and we'll just say that those kind of higher order relationships probably aren't having a large enough effect on the dynamics that we care about that we can just ignore them, and so we close the system at this pairwise. We can think about other approaches referred to effective degree. I'm not going to explain these. I just want to say the terms so that you're aware there are other approaches. And then an edge-based approximation. So if you're unfamiliar with network science, one of the things that network scientists love to do if things start to get hard is just flip the definition of the nodes and edges, and sometimes things get easy. And so one of the tricks that you'll often see people doing is saying, okay, well, I've defined individuals as the nodes and transmission as the edges. There's no reason that I couldn't do it the other way around and say that individuals are edges and the transmission events are the nodes. And maybe the math gets easier if I do that. And so one of the things that's actually very common for people that model traffic networks, that you'll see the edges and node definitions get flipped. And it, at least for me, causes my brain to melt out of my ears, and then I pick it up, put the brain back inside, and maybe I figure it out. But it quite often simplifies things dramatically. And so Miller and Kiss just review some of the things that we might care about, right? So one of the things that we might care about with these different ways of simplifying the systems is how many equations do we end up with as a function of the number of compartments and as a function of the number of unique degrees in the system. Because ideally, we might like an approximation that results in the smallest number of possible equations while capturing the maximum number of salient features. We might care about, is there known to be an analytic approach for estimating the final epidemic size? And then if we care something about calculating the early growth rates, how hard is that from a computational perspective, right? Is this something that we might be able to solve reasonably on a supercomputer, or is this something that we're not going to be able to solve even with as much supercomputing power as possible? And so these are the kinds of decisions that we want to make as we start to approach a modeling problem, right? So what do we think are going to be the salient features of the dynamics? What do we think are the most important features of the sociobiology that we need to be able to capture? How do we conceptualize that mathematically or computationally? And then how can we start to simplify? And the way we want to think, at least the way I think we should think about simplification, is how do we start to pare things down so that we reduce the complexity of the equations of the simulations as fast as possible while retaining all of the things that we think are important or that we want to be able to evaluate with data. And so that's why these kinds of boxes are so useful in these review papers, is that they help us kind of think through, okay, what's a tool that I can take off the shelf mathematically that will help me simplify this system of equations that's likely to result in a tractable number of equations for simulation or inference. Okay, but I still haven't answered the question yet. So why does influenza infect 500 million people and Ebola 30,000? Well, it turns out that part of the answer has to do with the role of super spreading. So I would say, like, if you're going to read 2 papers, and I'll list 5 papers by the end of the talk. If you're going to read 2 papers, I'd read the paper by Myers and I'd read the paper by Lloyd Smith. And Lloyd Smith's paper is not a network paper, but it uses one of the most important modeling paradigms for non-network infectious disease modeling, namely the negative binomial distribution. And for those of you that have not worked with the negative binomial distribution, I will tell you that I end up with a conspiracy theory style map behind me every time I have to figure out somebody's notation for the negative binomial, because every single paper seems to notate it differently. So if you start reading a paper like this and you wonder, why are they doing it this way? It's because that's how they were trained, and everybody's trained differently. And so what you'll have to do is pull up Wikipedia and get a pad of paper and write down, say, okay, here's how I understand the negative binomial, and here is how Antoine has defined it, and here's how I map on between the two. And that's literally something I have to do every single time I read one of these papers. So what happens? Well, we can think about ranking the proportion of infectious cases on the x-axis based on how many secondary infections they cause, right? And so in a homogeneous population, in that randomly mixing population, if let's think about a discrete time model where everybody that's infectious today recovers tomorrow. 50% of the people infected today infect 50% of the people infected tomorrow, 90%, 90%, 100%, 100%. You get this y equals x line that goes across the diagonal. As you have more heterogeneity in transmission, we see this curve bowing up and to the left, meaning that increasingly small fraction of the people infected today infect an increasingly large fraction of the people infected tomorrow. And this can be conceptualized with super spreading. Now, there could be a whole bunch of other reasons this could happen, but we might think about network heterogeneity as being a cause of this. And so we see diseases like smallpox, measles, and SARS having more and more and more infections resulting from a smaller and smaller proportion of the population. And you see that SARS and measles are kind of sitting around this sweet spot for a lot of complex system scientists, this sort of 80-20 rule, where you have 80% of the new infections resulting from 20% of the people who are infected today. We can map Ebola and flu onto this chart here. Flu is basically mass action. You're allowed to model flu. Peter can plug his ears. You're allowed to model flu with the SIR model, at least at the national level. Ebola is basically like SARS, where it has an R naught of 2, but it is completely dominated by super spreading events. So you imagine we go out and gather some data on the number of secondary infections. For flu, those data are going to look like 0, 2, 1, 2, 3, 2, 2, 2, 1, 2, 3, 4, 2, 1, 0. It's going to look like a Poisson distribution with lambda equal to R naught. Whereas Ebola, if we go out and gather data, it's going to be like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 50, 0, 0, 0, 0, 0, 10, 0, 0, 0, 0, 0. And it's not going to look like a Poisson distribution with lambda 2. It's going to look like a negative binomial distribution where you have 2 parameters that describe the distribution of secondary infections. And COVID, and this is the thing that is so insidious about COVID, both from a modeling and a public health perspective, is that COVID is just a little bit less reliant on super spreading events than Ebola and SARS. And that puts it at this kind of sweet spot where it breaks all of the models we have, even for Ebola and SARS, and it also breaks most of the conventional public health wisdom in the United States and Western Europe when it comes to responding to these pathogens. So is there a way from a network perspective that we can get a more realistic estimate of the final size? So one of the reasons we like the R naught is that there is, if you believe all the assumptions, there is a very simple equation for taking the R naught and estimating what fraction of the population is at risk for getting infected. So not only does the R naught allow us to compare models to each other, to estimate the epidemic risk, it also allows us to understand something about the total population size that might, or the total percent of the population that might get infected. So is there a way that we can relax some of these assumptions, but still keep those features of the R naught that we care about, or keep the resulting emergent properties of the R naught that we care about, namely that we can translate it into a measure of risk? So here are the assumptions. The disease results in complete immunity or death. The disease is transmitted in a closed population. All individuals are equally susceptible. Contacts occur according to the law of mass action, and a deterministic analysis is appropriate. And so in the work that we've been doing, the 2 things that we think are most important at least from a kind of a first pass perspective, is number 4, number 5, the network perspective and the deterministic analysis perspective. And so that's work that we did with Laurent and Antoine and Ben Althaus, who's not here. And what this work does is to say, okay, R0 is the average, the mean, it's the lambda for a Poisson distribution. And if the number of secondary infections is indeed Poisson, then the higher moments don't matter. We can fully describe the Poisson distribution with just the lambda. But if it's a negative binomial, well, there are 2 parameters, and we've got some higher moments to worry about. And if it is uglier than the negative binomial distribution, not that the distribution wouldn't be beautiful, I just mean there would be a lot more equations, we have many, many higher moments that we might have to care about. They can affect the final size in increasingly interesting, potentially, and dependent ways, such that how having a large kurtosis affects the final size is going to depend on the lower moments. So it kind of chains together. And so can we come up with a simple way, at least simple enough way, to take the higher moments, if we can estimate them, plug all those higher moments into an equation and get out a final size. And so that's what Antoine and Laurent developed, is this machinery for plugging in the higher moments and getting an estimate of the final size. And it turns out, if you're familiar with this, it's hard to estimate higher order or any kind of larger parameters associated with any distribution. So the mean, the first moment describing parameter, is pretty easy to estimate. Anything harder takes a bunch of data. And so here we're looking at an early paper by Ryu and Althaus, where they're estimating the R0 for COVID and the dispersion parameter K, which is how I typically conceptualize the negative binomial distribution. And so here's the other thing that hurts my brain about the negative binomial. Low K means that you have more superspreading, that the distribution has more heterogeneity. I call that over-dispersed, although in the biology literature, over-dispersed means that it's more homogeneous, which is, who knows why that had to be the case, but that's just what it means. So low K means there's more superspreading. High K means that there's less superspreading. As K goes to infinity, the negative binomial distribution becomes a Poisson distribution. In practice, any K larger than 9 or 10 is basically infinity. So if you estimate a K that's 7, 8, 9, 10, which is what it is for flu, then that's infinity. It's Poisson as far as any statistical test is probably going to tell you. The K for COVID is somewhere between 0.1 and 1 or 2, depending on who's estimating it. The best estimates now are somewhere around 0.5. So here on the x-axis, we can use this machinery to plot the proportion of susceptible individuals that are going to be infected at time infinity. Now, it turns out that even under these assumptions, which we call the Kermack-McKendrick assumptions because of the 2 authors that originally developed this 50 or 60 years ago, even with these assumptions, R infinity is something that requires some arguing about how you actually calculate it, because there's not a closed form way of calculating it in most cases. So we end up with a bunch of different ways of calculating that are all about the same in terms of their estimate in many cases. But so for COVID, if we just plug in the R0, we get an estimate that between 50 and 100% of the population is going to get infected. And this variability does not come from sampling or error. This is different estimates of the R0 in different populations. Best estimates around 80%. Now this circle here, these are estimates of the attack rate in places like Manaus, on cruise ships, fishing boats, places where we think you do have almost mass action mixing with respect to the social networks. They do experience these really, really high attack rates of COVID. It's one of the challenges with COVID-19. However, once we incorporate the super spreading in many other populations, the estimate of the proportion infectious drops to 10, 15, 20%. And that's in line with what we've seen in many populations as well. Now, we can do this for a bunch of other pathogens where we have estimates of the first and second moments. And the only reason I'm showing you this giant mass of lines and dots is because I want you to focus just on COVID and the difference between the red and all the other bars. So for COVID, the estimate under the mass action model is very far away from the estimate under the network models and some other kinds of approaches. For all the other diseases, there's actually quite a bit of overlap in the estimates. Now, we do see this trend of lower estimated final attack rates, et cetera, under the network models, incorporating the heterogeneity, but there's quite a bit of overlap, except for COVID, where you get this really big separation. So one of the reasons I'm saying that COVID-19 is a complex system that breaks our mental models, breaks our public health models, breaks our mathematical models, is that it turns out it is sitting at this sweet spot in parameter space that makes it very, very sensitive to differences in the network structure, to differences in the behavior, such that in some populations, COVID will infect 80, 90%. In other populations, it may only infect 10 or 20%. Whereas for lots of other diseases like smallpox, flu, MERS, SARS, Ebola, they infect roughly the same percentage of the population in many, many, many different kinds of populations. So while there's still complex systems, they don't feel the effects as acutely. And I realize I'm anthropomorphizing this disease, but like they don't feel the effects as acutely as COVID does. For diseases like flu, you can zoom in and zoom out, and a lot of those parameters that matter at the national level are going to disappear in terms of their effect as you zoom in. As far as I can see for COVID, as you zoom out from my house all the way up to the globe, those parameters at my house are still affecting the globe. Those parameters at my neighborhood, at my city, at my county, at my state, at the country, in our neighborhood of countries, that persists across these different scales in a way that is very unusual for lots of different systems and very unusual for many infectious disease systems. It's also one of the reasons I think this is such a rich opportunity for the kinds of work that so many of us do and are excited about. So I realize that I'm not going to cover most of the slides, so I'll just share the slides with everybody. But I'm going to kind of just finish up here, and I want to save at least 10 minutes for questions. I think I have until 15 after, if that's right. So there's a potential benefit to super spreading. So I want to kind of continue to close this loop between what we think of as interesting and fun math, what I admittedly think often as intimidating math that requires me to spend a lot of time re-educating myself on classes that I should have paid more attention to or should have taken in the first place, but also cool physics and fun computer simulations, but also then learning something about the biology and sociobiology of the pathogens, but then also learning something about public health interventions. So there's a benefit to super spreading, namely that if we can identify the individuals or the settings that are causing the super spreading or resulting in the super spreading, we can intervene to control the pathogen. So for Ebola, as soon as you have safe, respectful burials and you provide personal protective equipment to healthcare workers, you basically eliminate super spreading events and the disease comes under control very, very rapidly. Similar story for SARS. COVID's a little bit harder. It turns out for flu, there's basically nothing we can do until we get a vaccine. Most of our public health models are based on flu or Ebola, especially in the US and Western Europe, Canada. It's part of the reason why we have suffered so much for COVID is that COVID is not Ebola and COVID is not flu. So one of the things we could do is say, all right, well, what if we just curtailed super spreading events above a certain size? Now, I haven't defined super spreading event yet, and so I'll try to do that right here. So imagine here we have on the x-axis just the time evolution of the system is measured in kind of discrete generations of infection. So how long you go from somebody becoming infectious until they infect somebody else. For lots of different stochastic realizations of the model in blue, the expected trajectory in orange, the kind of exponential growth mass action style with the dashed red line, under with an R naught of 2.6, where we have different maximum gathering sizes allowed, from maximum of 10 to maximum of 100 to maximum of 1,000 to maximum of 1,000,000. So the 1,000,000 and the 1,000 are basically mass action. And then as we get smaller and smaller and smaller, this is not a network model per se, as much as it is a model where you have different gathering sizes, but we can start to think about the left-hand panels as network models. And what you see is that more and more of these blue curves turn over and fail to take off. And this is not because of interventions, we've just limited group sizes. We could think about that as an intervention, but the group size is limited in these simulations at time 0. So it's not something that changes, it's a feature of the system. And if we kind of squint, we say, okay, well, a million and 1,000, everything's going up. At 100, we start to see a lot of them come down, such that by kind of generation 6, it's on its way down, but you probably already infected most of the population by then anyways. And then when we get to size 10, you see almost none of them take off. And so it turns out for COVID, if you stop super spreading events of around 12 to 15 individuals, then the system should come under control on its own. And so that's how we could think about defining what is a super spreading event. Well, it is an average number of, it is a number of, not average, it is a number of secondary infections that's large enough that it's sustaining the outbreak. And so for COVID, that turns out to be somewhere between 10 and 20. And it's one of the reasons, it's actually very interesting that 10 to 20 comes out of this analysis and has been supported by a recent policy level analysis that came out in Science, where they looked across what policy interventions actually work for COVID. And the two biggest things that work aside from mask wearing are 10-person limits and closing the schools. And so it doesn't really matter if the restaurants are open or the movie theaters or the bowling alleys. What matters is if you have people mixing outside of their pods in groups of bigger than 10, because 10 is this magic number given the parameters of COVID, such that it can sustain itself in the population. And if we get that number down below 10, then it's going to die out in most populations. It's, again, one of the things with COVID is because it feels so many of these different aspects of the system so acutely, the local networks, the local behavior, the local susceptibilities are going to matter immensely. So it's not the case that you're going to have a global plane that's going to work everywhere. But there is good evidence, both mathematically and empirically, that you can intervene successfully. So there's a problem, and I'm going to kind of wrap up here. These models are all assuming the following: that an individual that is at high risk of becoming infected is also at high risk for infecting a lot of other people. In the network parlance, this would be that the in degree and the out degree are the same. That's the assumption in almost every network model that's out there. If I try to even do community detection, for those of you that don't know what it is, you're going to hear a lot about it in the next rest of your life. For most of the models for community detection, the code will literally just output an error message if you don't have the in degree and out degree equal to each other. If you're lucky, you'll get a warning telling you you really shouldn't be doing this, but we're going to give you an answer anyways. So we don't know that much. There's been a lot of great work, and some people on this call have led that work. So I don't want to detract from the fact that there's been a lot of really important work on this, but there has not been enough work, either empirically or computationally, mathematically, around what's going on when you have in degree and out degree not being the same. And these calculations that we've done previously, everything I've done up till now, and the effectiveness of public health interventions, all rely on this assumption that in degree and out degree are highly correlated, and that individuals who are at high risk of getting infected are at high risk for infecting other people. I can think of one system where I know that's not true for contagion, and that's Twitter, right? There are lots of people who follow lots of other people. I'm 1 degree away from, people that are super mega hubs, but they're never going to retweet the things that I retweet, right? And so the directionality of those connections matters a lot for Twitter in terms of the probability that something's going to spread, right? You might imagine a whole bunch of other reasons that this could break, right? So basically, for those of you that are more familiar with social network analysis, anything that breaks the friendship paradox is going to break basically everything. Well, not everything. One of the interesting things we show in this paper is sometimes it doesn't, but basically breaks everything that I've said up until now. So if you have a sortativity, it's going to break the friendship paradox. And that for sure happens on Twitter, and probably also happens out in the real world. So it turns out that the difference between in degree and out degree matters a lot in terms of the math. If the in degree is Poisson, that can be enough for the whole system to behave like a mass action model, or at least a whole bunch of the heterogeneity can disappear. And it matters a lot from the public health perspective, because our ability to identify individuals who are super spreaders or super spreading events relies on this friendship paradox, right? So one of the reasons why cluster busting and case investigation, reverse contact tracing, is so effective sometimes is that if I'm infected with COVID, it's much more likely under the high risk, high spread model that I'm connected to a super spreader. So if you go back and you find the person that infected me and trace outwards, you're going to identify this huge cluster. But if it turns out that I was at kind of high risk for getting infected, maybe, but I'm attached to people that are low risk. Maybe this is like patients, healthcare workers, for example, might be a good example of this, right? Where they're at pretty high risk of getting infected, but they may be at pretty low risk of ongoing transmission. You're not going to get as much bang for your buck as you do this reverse and forward contact tracing. Okay, so 2 minutes, I'm going to fly through this. The stuff that I think right now is super interesting for COVID are these metapopulation models and the effects of spatial structure. And so this is work that's been done a lot in the classical ecology literature. Turns out one of the papers we published that looks at crowding and the effect on COVID-19, the definition of crowding came from an Oxford professor, a zoologist named Lloyd in the 1960s. And the numerator for crowding is the expected number of contacts in a mass action epidemic model. It's not how it's defined in the paper in terms of how it's written down, but mathematically, it's the expected number of contacts in a mass action model. And so there's a lot of really cool work that can be done just taking these classical definitions for how people have thought about crowding and its effect on dynamical systems in ecology and imposing network structure on those models and seeing how things play out. But it's also been done quite a bit in the network literature. This is a great paper, one of the ones that should be on your list on dynamical patterns of epidemic outbreaks in complex heterogeneous networks. So it turns out that we know the consequences of a model that looks like this. And so this is relaxing that closed population assumption. So you have a little closed population, you have red nodes infecting blue nodes, and we know that it kind of looks a little bit like this. The infection, number of new infection cases in time goes up and it comes back down, and it's not really symmetric, but it's symmetric enough. However, the real world probably is most often conceptualized like this, where you have this hierarchical community network structure where you have households that are nested in neighborhoods that are nested in conglomerates, and it's nested in this bigger nest of all of these hierarchical structures. And it's not so clear what's going to happen as we play out a contagion process through this kind of network. Now, there are some papers that can help us think through this. One of them, and this should be on your list, is Kalitsa and Vespignani's work on metapopulation and heterogeneous coupling. The other, we'll hear from Professor Dodds later in the network workshop, is by Watts et al., where they look at multi-scale resurgent epidemics and a hierarchical metapopulation. You can kind of see their diagram looks like a slightly better, substantially better version of my cartoon sketches. But what they show is that if you have a single nice closed population, a single layer, you get a one wave. And as you have increasingly many layers, you get this smear. And it actually, I think, turns out that you have n-1 waves deterministically, and the smear is coming from the stochasticity in the model. But I would be interested to hear from Peter later if that's actually true and if anybody knows that. But you get this like broader and broader and broader epidemic duration as you have increasingly hierarchical structure that's present in the network. And so one of the things I would say, and there's people on this call that have worked on this, is the effect of higher order structure on epidemics is something that's not very well studied. The effect of clustering is fairly well known. There's some nice analytic results on that. There's been work on some push-pull complexes and other stuff that's come out very, very recently but both mathematically, but also empirically, the relevance is also a really big question. So if you're interested in higher order effects, either from a math perspective or from an empirical perspective, those are great questions to work on. Last paper I'll mention, and I'm wrapping up here in the next 10 seconds. This is probably, I think this may be the coolest paper that's ever written. It's by Professor Lisa Sattenspiel and Professor Deanne Herring, two anthropologists. They were interested in the same kind of hierarchical metapopulation structure. And they took logbooks from the Hudson Burr Fur Trading Company during the 1918 flu. And so you have fur traders in what is now Canada showing up at these trading posts, signing in. It's like Antoine Allard, 27 pelts, Laurent Dufresne, 3 pelts, on the date. And you see them getting sick as they don't show up, as they're replaced by different individuals. And so you have this kind of dynamic of people getting sick in these different trading outposts in these different parts of Canada during the 1918 flu pandemic. And they used it to parameterize a hierarchical metapopulation model in agent-based simulations. And they get these multi-wave epidemics in this deterministic model that matches what happened in the logbook data when it comes to the infections from the 1918 flu up in Canada, during what is now Canada during the 1918 flu. And so this is a really interesting paper about linking a very cool creative data set coming out of anthropological studies to agent-based simulations to classical, what is now really classical and fundamental theory in both network science, but also ecology. So there's a lot of really exciting work that can be done from this kind of starting point. And so the last couple of slides, one of the things then that researchers have been interested in is how can we quantify these smears? Well, one way we could quantify them is by just kind of looking at the width and height of the peaks of an epidemic. And one way that we might do that, very dangerous way we might do that, is just by calculating the Shannon entropy of an epidemic curve and calling that the intensity. So how sharply peaked it is versus how flat it is, we might be able to get an estimate of that using the entropy of the curve, thinking of them as kind of counts. And what it turns out is that for flu, areas that are larger urban conglomerates have broader, flatter epidemic curves. And we see the same thing for COVID. This is the paper we published on crowding and epidemic curves, that across China, the crowding, which is our measure of how urbanized or how big the urban conglomerate is, more crowded places have flatter, broader epidemic curves, whereas less crowded places have sharper peaked epidemic curves. The distinction in my mind is Sao Paulo versus Manaus, where in Manaus you have an isolated, larger population with close-knit structure within the city that leads to a very sharp peak, and it's a bit of a stochastic waiting game until it shows up. So it takes some time until it shows up in the rural areas, but then you have a population structure that's very conducive to sharp peaks. Whereas in these larger urban conglomerates, it shows up very early, but it takes a long time as it bops around very slowly from neighborhood to neighborhood to neighborhood. And you get these broad epidemic curves. We show the same thing in Italy. And it turns out this log-log relationship between the inverse Shannon entropy of the curve and the mean crowding holds over 4 or 5 orders of magnitude, both in terms of the epidemic size and the crowding, explaining both what happened in China, where you have huge cities and very little in terms of COVID, and Italy, where you have comparatively small cities and massive COVID outbreaks. So I think there's quite a bit of interesting work that can be done in this space. And one of the ways we got started by doing this is work that was in the paper led by Allison Hill, was we just conceptualized a simulation model where we can have different kinds of community or hierarchical structure, different layers in this case, and then see how this plays out. And I'm going to end right here, which is, here's what I think is interesting. Well, I think all this is interesting. But so here we have a no intervention model, a sparse single layer network with this one wave. On the right, we have a no intervention model in a multi-layer network where you get this kind of smear that goes out. As soon as we intervene, you get a flattening and a compression of the single layer curve, but you actually get an intensification, a sharpening of the multi-layer curve. And what happens here is that individuals go into their households, they spend a lot more of their time in the household where the contact density is higher, and they transmit really, really fast and the epidemic burns out. But you get a bigger burst of infections that happen really, really quickly right around the time of the lockdown. And so you get this like spike as you lock down and all these household transmissions happen, and then it dies out really quickly. And so the effect of the interventions, whether you're actually broadening and flattening the curve or sharpening and intensifying the curve, matters in these very simple models, whether we're dealing with this hierarchical structure or not. And so I think there's a lot of very, very rich work kind of understanding how realistic this is and what we can do here. All right, so I'm going to skipping all this. Unfortunately, I'm skipping over this awesome paper with John Gabb where we show that, what do we show? We show that you can't tell the difference between complex contagion models like the voter model and interacting pathogens. The message that John Gabb and Laurent like, which is a positive message, which is that we can use the complex contagion model to study interacting pathogens. The message that Sam likes is nihilistic, meaning that in the absence of additional data, we can't tell the difference between whether it's a complex contagion or an interacting pathogen. And so we need to bring our empirical knowledge and data to the question of whether a Twitter meme is spreading in a particular way because it's interacting with other memes, or whether it's because it's following some kind of complex contagion or not. So and it's freezing. So, okay. So the last thing then is, importantly, COVID-19, like all pathogens, this is particular to the United States, although we could swap out different indigenous groups or other marginalized groups in different populations. COVID is hitting Black and poor communities the hardest, underscoring the fault lines in access and care for those individuals on the margins. So the results of racism and xenophobia in the United States are leading to massive disparity in terms of the effects of COVID-19. We're seeing this also play out in terms of the prisons and incarceration. And so I'm quoting from this paper, this blog article by Grace Noppert. This would be the last thing I'd encourage you to read. As the epidemic continues to ravage the American public, an unsurprising story emerges. Poor communities are hotspots for COVID transmission. The death rate is staggeringly high among African Americans compared to whites. 14% of Michigan, for example, is Black, but 40% of the deaths are Black. The Black community in the United States crossed over this 1 in 1,000 fatality threshold months and months and months ago. And so as we're thinking about how we model these systems, how we model the public health interventions, how we think about the prioritization of vaccines, we have to take account of the fact that there is inequality that results from our societal values as they pertain to racism and xenophobia and the effects of all of these on these different communities. And we have to account for those as we're modeling these systems and as we're then connecting these systems back to public health interventions. And so COVID-19 became a pandemic because the world doesn't understand complex systems and networks. It's why I'm so thrilled that all of you are here. It's why I think that it's a continual learning process and a continual exploration process. It's one of the reasons that I so strongly agree with Laurent's philosophy that this is one of the most exciting and rewarding fields to work in, because our understanding is constantly challenged and constantly brought to the forefront as we're continuing to deal with generational crises around contagions, whether those are fake news or COVID, or whether that's climate change and its effects on the eco-evolutionary dynamics of pathogens, plants, animals, whether that's dealing with human society and how we're going to deal with these effects of racism and xenophobia, how we're going to move forward collectively, hopefully as a global civilization. So I think there has never really been a time that we can do more as complex system scientists because of the data that are available, because of the techniques that are available, because of these foundations we're sitting on, and it's never been more important. So thank you all very much. And I do actually, amazingly, I think, have a few minutes for questions. So thank you.
All right, I'm gonna ask everybody to unmute themselves and give Sam a big round of applause.
And we can have more than a few minutes for
Yeah,
questions.
let's take about like 10 to 15 minutes for questions.
As much as needed, of
Yeah.
course. Maybe I'll get it going, but I should just say, feel free to jump in, or you can use the chat, raise your hand if you have that feature on your Zoom. Any way that you want to ask your question is going to be okay. I'll ask a first question. I wanted to tie sort of what you presented today, Sam, with your background in evolutionary biology. I think what you presented help us, debate different strategies to help us fight against COVID, help us debate whether or not, going for a herd immunity strategy is a good idea. And I'm curious about how the evolutionary biology of COVID and risk of emergence of new strains tie into this. Like, how can we quantify risks of future pandemics into how we fight current pandemics?
Yeah, so my favorite paper on this is also by Allison Hill. It's in Nature Communications. It's on the probability of higher strain emergence, the emergence and persistence of more transmissible strains in a network. And so if you think about like a heterogeneous degree distribution, the transmissibility is going to have to overcome the fact that the degree distribution has been homogenized and the epidemic probability is lower for new strains as a result of the pathogen moving through the system. And so it turns out to be really non-trivial, even in the most basic models, to understand what is the probability that a more transmissible strain would both arise and then be able to spread during an epidemic. And that's actually, so I was hoping I'd be able to talk about it today, but we're still kind of finalizing everything. It's obviously gotten a lot more politicized now, so we're kind of moving very, very slowly. But I'm skeptical that we really understand this B117 variant in terms of its transmissibility, because it arose basically and started spreading as soon as the lockdown changed. We were looking for it like crazy. We don't have very good surveillance in most places, and so the sampling is just a mess to figure out how to disentangle all that. And so all of these different features that I've talked about so far are going to affect our ability to, I mean, arguably means that we can never really say that it's this much more transmissible and separate out, like integrate away all of the other things that are affecting the transmission of those variants. So the first answer to the question would be that it's really hard to even answer the question right now about whether a new strain really is more infectious or not, or whether it's just the initial conditions, what they call the founder effect in genome biology. In terms of the evolution of resistance to the vaccine, this is one of the cases where there are thousands of papers on simple models that nobody thinks they're appropriate for the current situation that we're in. One of the things that matters from a sociological perspective is that the mRNA vaccines can be updated really, really quickly. So if we're monitoring for it, we should be able to update the vaccines. But I actually think this would be a really great question to work on. And I know Laurent and I have spent quite a bit of time thinking on this and not yet successfully finalizing a product on it. Is, you know, we can conceptualize from a network perspective the way in which a virus might explore phenotypic and genotypic space, and how different selective features that it encounters, like a vaccine, like different social network properties, may affect the way it is exploring that space, and how that could then translate into it landing in an area where it would be resistant to a vaccine. So I think there's quite a bit of work that could be brought to bear on this problem. I do actually think this is one of the cases where I'm convinced that deep learning would actually have quite a bit of useful application, right? So you think about, like, what is antibody binding? It's pattern recognition. And like, what is my crappy understanding of deep neural networks? It's pattern recognition. And so like, I think this is, and there's a lot of data. So I think this would be a really interesting opportunity where we could bring to bear some of our network science expertise with respect to machine learning and genome evolution. Actually, just the last thing I'll say before I take the next question is, if you said, Sam, what is the one thing that network scientists should be doing that they're not doing right now? That's deep learning. And the reason being is that it turns out that, like, there's this massive paper that totally obliterated all of computer science when they showed that label propagation was better than what they were doing currently when it came to graph neural networks. And it's like, well, yeah, but we have known that for 30 years in network science. And it's like, literally, the deep learning people are discovering stuff that is in the first chapter of Newman's book, basically, when it comes to network science. And there's just not very many network scientists that are really kind of jumping into this. I'm sure there's some people on the call that are rolling their eyes and saying it's just because I don't know enough, which is probably true. But some of you can get involved more on that, which I think would be awesome.
Well, some hands got raised. I don't know if it's in relation to your last comment, but Bridget, did you have a question?
Yes, thank you very much for your presentation. And I'm working through a lot of the ideas that you brought up, but I wonder if you could maybe work through some of the effects of the specific moment in history in which we're looking at these events, these epidemics, and whether it is possible to consider those contingencies. I mean, I'm thinking of the flu epidemic of 1918 and super spreading events, and the fact that we are talking about a period of World War where, for all intents and purposes, super spreading is kind of an unavoidable event. Whereas with COVID, we could perhaps argue in many cases that these super spreader events are happening more by choice than by kind of historical necessity. Whether the rise of not just the anti-vax movement, which we know is historical, but its alliances with other political groups may impact the ways in which the disease spreads, things like that. Like I'm just thinking about whether historic contingencies can be represented in these networks or affect the overall trends of the patterns you're seeing.
Yeah, that's a wonderful question. And I'll restate, just not at all trying to say it as completely and eloquently as you did, but just that, like, how do we deal with the initial conditions and in the historical contingency? I will say that I am very pessimistic on this. I think that there's compelling evidence that you can't do it very efficiently, that it's really, really hard to, unless, and this is why I think the collaborations matter and why I think workshops like these are so important. If we can use our understanding and expert knowledge and additional data sets, we can, I think, come up with creative ways of appropriately parameterizing these initial conditions, either qualitatively or quantitatively, and then studying the system as it evolves forward from those initial conditions. I don't think that there's a way that we can separate out the fact that Donald Trump was president of the United States from what happened with COVID-19, right? Because the CDC historically has played an important international role in kind of galvanizing responses and both publishing literature on, cases and where they come from and all this. So I really don't think we can pull that out and just say what would have happened if, in any kind of simple way. I think we could do it very eloquently, both quantitatively and qualitatively, but it's going to require bringing to bear our understanding on the kind of sociology of the CDC and populist movements and fake news. And so we'll hear from Professor Brooke Foucault-Wells later and others who have this kind of expertise of thinking about the way in which we might conceptualize the importance of these different kinds of events. But I think it's exactly why I think we should all be here, and why this is such a hard problem to work on. You mentioned 1918 flu, and I'll tell you that, like, the most interesting thing that I have learned in the last 6 months. So I reviewed Christakis's book on COVID, and he said a bunch of stuff that I didn't agree with. But one of the things that I was like, this cannot be true, or it's something that you can't really falsify anyways. But he said that literature has not covered pandemics very much. And I kind of dug into this and I was like, there's no way this is true. This cannot be true. And there's like a lot of really famous works in the Western canon that are sort of about pandemics, but they're really, everybody thinks they're metaphors for something else, right? Like the rise of fascism and other sorts of stuff. And one of the things that I encountered was this hypothesis that the beginning of Mrs. Dalloway by Virginia Woolf is not about the end of World War I. It's about the end of the 1918 flu pandemic and reveling in the mundane and being able to go shopping and doing all those sort of normal things. And so I was reading Virginia Woolf's essay on having the 1918 flu, and she starts by saying that illness is undercovered in literature, basically because literature is about the mind and the soul and not about the body. And it turns out, I was talking with Ed Young at The Atlantic apparently published 0 articles about the 1918 flu back at the time. And so why am I rambling about this, aside from saying something that I think is really cool? Well, how do we, I'm saying that the collective societal effects of SARS were organizational with respect to the response in South Korea, Vietnam, Thailand, China, Taiwan, Japan, et cetera. What happened to our collective experience in 1918? Well, how do we remove the fact that we seem to have so little documented societally about the 1918 flu? I think it's probably because of the trauma of World War I and World War II and how that kind of dominated all of our thinking, both from a literature perspective, but also from a historical perspective. I don't even know how we separate that out from where we are right now from a public health perspective, much less figure out why Donald Trump is here and what that meant in terms of both the U.S. response, but the international response.
I think we can take another like 5 minutes to keep questions going. Nicholas, I think you had a question.
Yeah, so one of the things, and this is going back to, I think, Laurent's question and Sam, your first reply, it sounded like you were saying that network models would potentially make different predictions in terms of the virulence transmission trade-off. So like that is a thing that I've studied, and it's like the intersection of evolutionary biology and epidemiology, and it's a little bit contested. So I'm kind of curious because it, like I said, it sounded like you were saying in a network model, you might expect to see something different. You know, and within the context of COVID-19, you know, this idea of surveillance and more virulent strains, and like, what do we expect, and so on and so forth.
Yeah. So first, I would say that one of the things I have a number of really bad habits that I'm aware of. One of them is that I kind of ramble real fast, and it sounds like I'm not picking my words very carefully, and then it turns out that I said it might and interesting, not that it actually would and that it would be relevant. So I think that you're right that the models of evolution of virulence are highly debated, both from a theoretical perspective, but also from an empirical perspective. And it's not at all clear whether they would bring anything useful to bear on the particular problem that we're dealing right now with COVID-19. But I do think that they motivate a bunch of hypotheses that we might be able to test, either about our understanding of the evolution of virulence from a theoretical perspective, as we're watching COVID play out with this kind of unprecedented data set, or whether it might actually be the case that we could bring something in to the problem. I guess if I was going to approach it right now, the first thing that there's two things I would start doing. One is that Jesse Bloom, who's a professor at Hutchinson Cancer Center, mapped out all the mutations that affect antibody binding for non-SARS coronaviruses, or one of the non-SARS coronaviruses. And that might be an interesting data set to start looking at the connectivity of those different mutations and how they affect antibody binding, and get a sense for what the network structure looks like. The second is to take this in versus out degree and see if we start to layer in some of these things into the evolution of virulence models that we know can affect the epidemic dynamics, how that affects the outcomes of the evolution of virulence. I know a lot of this has already been done, and so I'm kind of demonstrating my lack of expertise when it comes to the current state of the literature there. But I do think there are things about COVID that will motivate, if they're not already done, modifications to or changes from the standard models. But yeah, maybe just to restate, I totally agree with you that if I'm going to be a Bayesian, which I usually am, I would put a very strong prior distribution on most of what we know or think we know about the evolution of virulence as it pertains to evolutionary dynamics as not being particularly relevant for COVID, or at least be very, very hard to figure out how to make it relevant.
Cool. Thank you. And also, like, I'm very keen on this. So if you would be at all interested in talking more, I would love to get a few minutes of your time in the future.
Yeah, that sounds great. And there's a really good chance that Laurent may be sending you a data set later to work on, because we have something that he's had an incredible student that's worked on it too, but we've got a couple of things bouncing around that we've never really kind of formalized. So it might be fun to think about a group on that for this workshop.
I see one hand raised. I also want to bring up, we're 20 minutes away from the next seminar. So if you need a human break, like, feel free to, get off the call or go walk around. But I also want to make sure that people can ask questions and chat. So if Sam, are you still available for 5 or for 2 minutes?
Yeah, I've got a 10:30, so I've got 5 minutes, and I can be a couple minutes late to that, but.
Okay, so I can't remember who had their Hayes ran, but if
I think it was me.
Okay, if you want to ask a quick question, and then we can,
Yeah, just not being in the field, you'd mentioned this big assumption that had relied that the results were derived based off. I just wanted to clarify: was that just that the graphs were directed versus undirected? Is that really what it amounts to?
It's a little bit bigger than that, which is that most of what I said as I was going through relaxing a lot of the other assumptions around epidemic dynamics as it pertains to super spreading are still pretty contingent on this assumption that you have in degree and out degree correlated with each other, or that the friendship paradox in the network is going to hold, meaning that your friends have more friends than you do. And so if you have in versus out degree separated, meaning that they're not equal to each other, or if you have a situation where you have anything else that's going to break that friendship paradox, like degree correlations, in terms of assortativity. So like high degree individuals are connected to high degree individuals. All of that kind of stuff is going to break the things I said, sometimes in interesting ways, sometimes in boring ways. And we know a little bit more now about what kinds of things happen mathematically. I think there's still a lot of really interesting work to do there, especially on kind of higher order models. We know a lot less, I think, empirically about like, is the in degree of risk similar for the out degree for COVID? Is that like, can we make that assumption or not? How do we even go about gathering data on that? I think for social networks, maybe that's a place where we could start looking at that kind of thing. So yeah, I think that's the answer.
Cool, thanks.
It's great, thank you. There's also really cool discussion going on in the chat about our need for stories around pandemics and what that might mean. So I think we can continue the discussions on Slack and whatnot, and let Sam move on to his 10:30 meeting. So if you can join me in thanking Sam Scarpino again, thank you.
Thank you all very much. This was great.
Let's take a human
Sam.
break. See you
Sam.
in
About
15 minutes or
minutes.
so.